we shall see some concepts about PN junction diode. So we shall start with electronics. Electronics is the field of science and technology that deals with the behavior of electric currents in electronic devices, components, in systems and equipments. So it started with vacuum tubes in 1961 and then ICs and then VLSI, vacuum tubes, ICs, transistors, before the transistors, diodes. So all these were under existence. So we can fabricate millions of components in one single chip. So the applications of electronics include communication and entertainment applications, instrumentation and control applications, defense application and applications in medicine, etc. So here we know in electronics we have three types of materials. We have the semiconductors, insulators and conductors. Semiconductors, the gap between the valence band and conduction band is very less, so that there can be movement of electrons from valence band to conduction band. Semiconductor example are silicon and germanium. So there may be that's a very small energy gap, nearly 1 electron volt in semiconductors. In conductors, they easily conduct current, so there is overlapping of the bands, valence band and conduction band. So this is the valence band and conduction band. There is overlapping of band, so there is free movement of electrons and holes. Insulators, there is a large energy gap between the valence band and conduction band, so that there is no free movement of electrons from valence band to the conduction band. So here semiconductors, we have the band gap 1 electron volt is sufficient, so that when we give any external electric field or we increase the temperature, there is possibility of movement of the charge carriers, electrons from valence band to conduction band and conduction band to valence band. Example of insulators, we know it is plastic, and conductors, copper cables are examples. So semiconductors are the most suitable components for all our electronic devices. Semiconductors are now classified as intrinsic semiconductors, which are pure form of semiconductors, and extrinsic semiconductors, which are impure form of semiconductors. We add impurities. So extrinsic is again classified as N-type semiconductor and P-type semiconductor. So in case of germanium and silicon, we have 4 valence electrons for germanium. So it can attach with 4 other germanium atoms like this. So it can attach with 4 other germanium atoms. So when there is impurity added, the number of valence electrons changes. So intrinsic semiconductor, in case of pure germanium, in intrinsic for germanium the energy gap is 0.72 electron volt, and for silicon the energy gap is 1.1 electron volt. So in a semiconductor we have anode and cathode. So a diode looks like this. So this one is anode and the negative side is called cathode. Anode is positively charged and cathode is negatively charged. Semiconductor current is because of movement of electrons and holes inside the semiconductor. The Fermi level EF lies exactly in the center for intrinsic semiconductor. The Fermi level lies exactly in the center between the valence band and conduction band. So EF lies in the center and EF is equal to Eg by 2, where Eg is the energy of an electron in conduction band. Now we go for extrinsic semiconductor. In extrinsic semiconductor, dopants are added. We add 1 part in 10 to the power 8 parts of atom in extrinsic semiconductor. So we have either for N-type we add pentavalent impurities, which has 5 valence electrons. Example arsenic, antimony and phosphorus. So these are called donor atoms since they donate one electron for current conduction. It donates or contributes one electron for the connection. So next we have for p-type, trivalent impurities are added which has 3 valence electrons. Example are gallium, indium, aluminium, boron, etc. So these atoms are called acceptor atoms. There is a free hole which can accept an electron for current conduction. So this is about n-type and p-type. In n-type, we have the valence band and conduction band, and the Fermi level line lies near the conduction band for n-type. Fermi level line EF lies near the conduction band for n-type, and here we have another imaginary band called donor level. The Fermi level line lies near the conduction band because it lies near the place where more charge carriers are there. Here more charge carriers are there near the conduction band. There are more free electrons since it's n-type, pentavalent impurities are added. Those free electrons with very less electric field can go to the conduction band. So more charge carriers are there in the conduction band. So Fermi level line lies near the conduction band for the n-type of semiconductor. And for p-type of semiconductor, we have a line called acceptor line or p-type semiconductor. Similarly, we have the valence band and conduction band. The Fermi level line EF lies near the valence band, and the line imaginary line near the conduction band is called as acceptor line. The conduction in p-type is called deficit conduction, and the conduction in n-type is called excess conduction. So here in n-type we know the majority carriers are electrons and the minority carriers are holes. In n-type, majority carriers are electrons and minority carriers are holes. In p-type, majority carriers are holes and minority carriers are electrons. So there are mobile charge carriers and immobile charge carriers, mobile ions and immobile ions. So these movement of electrons, holes and mobile ions constitute for current conduction in a diode. So conduction in an intrinsic semiconductor, we have drift and diffusion current. Drift current and diffusion current. So the total current in a semiconductor is because of this drift and diffusion current. So total current in semiconductor is equal to drift current plus diffusion current. So drift current is the movement of charge carriers, electrons and holes because of applied electric field. So this can be written as J is equal to Q N mu N E plus Q P mu P E, where J is the drift current, Q is the charge of the electron and hole, N and P number of electrons and holes, mu N and mu P mobility of electrons and holes, E is the applied electric field. So diffusion current is the movement of charge carriers from high concentration region to low concentration region. So take this is a P type of bar, and X increases, it's more concentrated here and less concentrated in the sides. So as X increases, the concentration reduces. So J is written as J is equal to minus Q dP dP by dx minus Q dN by dx, where Q is the charge of the electron and hole, dP and dN are diffusion constants, and dP by dx is the concentration gradient. As X increases, the concentration reduces, so there is negative sign in both the currents for diffusion current equation. So the total current in a semiconductor is the sum of drift current plus diffusion current. So this is drift current, which is because of movement of charge carriers because of applied electric field, and this is the equation for diffusion current for electrons and holes, which is due to the change in concentration gradient inside the bar. So drift current. So further, number of total current because of electrons is Jn mu n E plus minus Q dn dn by dx, and the total current because of holes is Qp mu p E minus Q dp dp by dx. So next we have mass action law. The mass action law states that Np equal to Ni square. So that is the number of electrons into number of holes in a semiconductor is equal to the carrier concentration square. Ni is the intrinsic carrier concentration. And then we have charge neutrality, which means the charge total charge is neutral. So the total number of positive charges is Nd plus P, because the number of donor atoms plus the holes, because donor atoms, when it moves from its place, negative ion, positive ions are created. And the number of negative charges per meter cube is Na plus N, which is the number of acceptor atoms which contributes to negative ions, and the number of electrons which are negative electrons. So the total number of positive charges is equal to the total number of negative charges in a semiconductor. For N type of semiconductor, the number of holes may be neglected, so Nd is equal to N, and for P type of semiconductor, the number of electrons may be neglected, so P is equal to Na. We have a concept called carrier lifetime. Carrier lifetime is the time for which on average a charge carrier will exist before recombination with a carrier of opposite charge. The value is from nanoseconds to the hundreds of microseconds, and it depends on the temperature and impurity concentration in the semiconductor. Now we shall see about the forward and reverse bias of PN junction diode. So in P type and N type material are combined together, we have the region called the PN junction diode. In between the P and N junction, without any biasing, we have a region called space charge region or depletion region or transition region. So there is some movement of holes from P to N and N to P, and beyond some threshold limit there is no movement of charge carriers. So the magnitude of threshold voltage, the potential difference for germanium is 0.3 volt for germanium and 0.7 volt for silicon is the threshold voltage. So if there is more concentration of holes, so here P, when holes move from its place, negative ions are formed here. Electrons move from its place, positive ions are formed near the depletion region in the N side. So now we go for forward and reverse bias. In forward bias PN diode, the P side is connected to the negative of the battery and N is connected to the positive of the battery. So we have the anode and cathode. Anode connected to the positive of the battery and cathode is connected to negative of the battery. So this is the initial barrier potential for the unbiased PN junction diode. So as we increase the forward bias, the holes from here gets this positive charge and holes here, so it gets repelled by the positive of the battery and goes towards the N side. Electrons gets repelled by the negative of the battery, goes towards the P side, and some recombination happens here. So the depletion region reduces in PN diode in forward bias. So the barrier potential is like this. And as we increase the in forward bias voltage, there occurs some time where there is no space charge region at all, and there is free movement of electrons and holes from N side to P side and P side to N side. And we go for reverse bias. P is connected to anode, P side is connected to the negative of the battery, and N is connected to the positive of the battery. This is the initial barrier potential, and this is the potential after the reverse bias. So in the reverse bias, these holes, majority carriers holes gets attracted towards the negative of the battery. These majority carriers electrons gets attracted to this positive of the battery. So the minority carriers electrons in the P side and minority carriers holes in N side are responsible for current conduction in reverse biased PN diode, and that is the reason we have the current I0 reverse saturation current I0 or IC0 is a very small current and it is in microamps range. So that is the depletion width increases in the PN junction diode in reverse bias. In breakdown happens in the diode. The IC0, the reverse saturation current value is less than 1 microamps for silicon and greater than 10 microamps for germanium diode. Breakdown happens, so when reverse bias voltage increases, the velocity of the minority carriers crossing the junction increases. The greater the reverse bias voltage, the electron moves faster, the velocity increases, the kinetic energy increases, and breakdown happens in the reversed bias PN junction diode. So the volt ampere characteristics, so in forward bias is drawn for VF and IF. As we increase the forward bias voltage till the cut-in voltage 0.7 volt, it does not conduct, and after that it starts to conduct slowly. Reverse bias is drawn for the reverse voltage VR and reverse current IR. Same way, as the voltage increases, current slowly increases and then starts to increase rapidly. So this is the volt ampere characteristics for PN junction diode and reverse bias. So these are some of the basic concepts in PN junction diode. Thank you.